Hello. With this video, I'd like to begin our fairly long unit on chemical bonding. This unit is based on all of Chapter 8 and part of Chapter 9 in the textbook. I'd like to present you with an outline as I have rearranged the order of the topics somewhat in a way that makes more sense to me. From Chapter 8, we'll begin with Section A, which involves classification of chemical bonds. That's the topic of this video. In Section B, I'll talk in a bit more detail about ionic bonding. In Section C, we'll review Lewis structures. In Section D, we'll talk about covalent bond energy, a new topic. And in Section E, we'll talk about VSEPR theory and molecular polarity. From Chapter 9, we will talk about hybridization and the localized electron model. So let's begin with classification of chemical bonds. As you'll recall, there are two limiting types of chemical bonds. Ionic bonding, which involves electrostatic attraction among large numbers of cations and anions in a crystal lattice, and usually occurs in bonding between metals and nonmetallic elements. And here's a depiction of the crystal lattice of silver 1 bromide. At the other extreme is covalent bonding, which involves sharing of pairs of electrons between two nuclei, and usually occurs in bonding between nonmetallic elements, that is, nonmetals and metalloids. Here's a depiction of the formation of the hydrogen-hydrogen covalent bond in the H2 molecule. As you can see, the hydrogen atoms begin far apart so that there is essentially no interaction between them, but as the atoms begin to move closer to one another, they begin to interact. Namely, the electron of one hydrogen atom begins to feel the electrostatic attraction of the nucleus of the other one. Ultimately, we reach an optimum distance that minimizes potential energy so that the two shared valence electrons can simultaneously feel the electrostatic attraction of both hydrogen nuclei. We can actually graph potential energy as a function of internuclear distance. In this diagram, we have potential energy on the y-axis and distance between the two hydrogen nuclei on the x-axis. At very large distance, the energy of interaction is essentially zero. As we begin to bring them closer together, however, you can see that the potential energy begins to decrease, again, as the electrons of each hydrogen atom begin to feel the electrostatic attraction of the other nuclei. And at a potential energy minimum, we have the lowest possible energy. If you start to push the nuclei closer together, however, then the potential energy begins to increase as nuclear-nuclear repulsion takes place. At the bottom of this potential energy well, we have two numbers. One is the bond energy. It is the energy released when the bond is formed in kilojoules per mole, or conversely, the energy required to break the bond. We also have the bond length, which is the distance between the two nuclei at minimum potential energy. So you can see for the hydrogen-hydrogen bond, the bond energy is 458 kilojoules per mole, routinely given as a positive quantity, and the bond length is 0.074 nanometers, or 74 picometers. There are two types of covalent bonds you'll remember. A nonpolar covalent bond in which the electrons are shared equally, for example in the carbon-carbon bond, and the polar covalent bond in which the electrons are shared unequally, as in the oxygen-hydrogen bond. You can see in a polar covalent bond, one end of the molecule, the one in which there is a buildup of electron density, is assigned a partial negative charge. The other end of the bond, and where there's a deficiency of electron density, has a partial positive charge. So the question is, how do you predict whether a particular pair of nonmetallic elements will form a nonpolar covalent bond or a polar covalent bond? Well, as you'll recall, you will look at the electronegativity difference between the two elements. So let's review electronegativity. Electronegativity is defined as the measure of the tendency of an atom in a bond to attract shared electrons toward itself. We come up with electronegativity values by assigning the atom with a partial negative charge a higher electronegativity value. Let's look and see at some periodic trends. On this periodic table, we can see that the most electronegative element, fluorine, with a value of 4.0 is in the upper right-hand corner. The least electronegative element, francium, with a value of 0.7 is in the lower left-hand corner. And as you can see, electronegativity increases from left to right in a period and decreases from top to bottom in a group. They follow pretty much the same trend as ionization energies, and it's probably related to the same features. So, to classify a covalent bond as polar covalent or nonpolar covalent, we will simply find the magnitude of the difference between the two electronegativity values. If it is less than about 0.4, neither atom in the bond really wants to attract the shared electrons toward itself more strongly. We'll call that a nonpolar covalent bond. On the other hand, if the electronegativity difference is greater than about 0.4, then there is a substantial disparity in electron attracting ability, meaning that one end of the bond will have a partial negative charge, the other will have a partial positive charge, and we call that a polar covalent bond. The more electronegative atom has a partial negative charge, the less electronegative atom has a partial positive charge, and if we are comparing the polarity of two polar covalent bonds, the one with the greater difference in electronegativity would be considered the more polar. So for example, if I look at these 5 chemical bonds between hydrogen and hydrogen, sulfur, chlorine, oxygen, and fluorine, we assign electronegativity values, we calculate the differences, and we can see that as the difference increases, the bond becomes more polar. HH is nonpolar because the electronegativity difference is 0. The fluorine-hydrogen bond with an electronegativity difference of 1.9 is about the most polar bond you can have. One point that I'd like to make is that when we describe bonds as being ionic and covalent, those really are limiting bond types on a continuum. And it is actually possible to calculate the percent ionic character of a bond by taking the measured dipole moment, dividing by the calculated dipole moment, and multiplying by 100. And what you see is that as the electronegativity difference increases, the percent ionic character increases as well. Our definition of an ionic compound is one that conducts an electric current in the liquid phase. So if you melt it and it conducts current, that must mean it's made up of ions. Now, let's do some problems. Using only periodic trends in electronegativity, let's predict which bond in each of the following pairs is more polar. Well, carbon and fluorine are further apart in the second period than nitrogen and fluorine, which means there will be a greater difference in electronegativity values. So I'll choose that as the more polar bond. Antimony and chlorine are further apart than antimony and iodine. That will be the more polar bond. And as you can see, phosphorus and oxygen are further apart than nitrogen and oxygen, so that will be the more polar bond there. Which of the following incorrectly shows bond polarity? Show correct bond polarity for those that are incorrect. So let's look at these. In A, we have a partial negative charge on fluorine and a partial positive charge on hydrogen. That looks good. In B, we have the partial negative charge on iodine, when iodine is actually the less electronegative element. So that's wrong. And to make the polarity correct, I will simply switch the positive and negative. In C, I have a partial negative charge on sulfur, partial positive charge on silicon. That looks good. In D, I have partial positive charge on bromine and a partial negative charge on bromine. Well, that's clearly wrong. So for that one, I'm simply going to cross out the polarities because that's a nonpolar covalent bond. In E, I have a partial positive charge on oxygen and a partial negative charge on phosphorus, which is incorrect. Oxygen is more electronegative than phosphorus. So I'll simply switch those as well. Finally, rank the following bonds in order of decreasing polarity. Open a periodic table and look and see and use the trends. And we will see that the most polar bond is the tin-chlorine bond because they're furthest apart. The least polar bond will be the sulfur-chlorine bond. The second most polar is the silicon-chlorine bond, and followed by the phosphorus-chlorine bond. And in our next video, we'll look at ionic bonding in more detail.